As if chemistry didn't have enough math already, let's look at the arithmetic of equations and dive into stoichiometry. Well, first off, define stoichiometry. Stoichiometry is the calculation of quantities when you're looking at chemical reactions and the products and reactants. Essentially, it's a way of doing math better in chemistry. So be able to balance chemical equations. Remember, chapter 11.3 was about that, and you're going to want to kind of look over chapter 11 in general to remind yourself how to balance these things. Be able to use chemical formulas. Remember chapter 9 with the polyatomic ions and such. Good time to brush up on that so you can predict quantities of atoms. List the applications for balancing chemical formulas. We're going to go over a few of those. Mostly it's how would you do math if. And we're going to put this in terms of the Haber-Bosch process. So a little bit of background on this. Ammonia is something you find naturally in guano and natural deposits. Essentially, nitrogen gas is present in the air, but nitrogen gas isn't really useful for much. It's very non-reactive. So ammonia, on the other hand, is what's called fixed nitrogen. And ammonia can be used in things like fertilizer or in munitions and explosives. And during World War I, Germany needed a lot of ammonia. So before this, actually, there was a lot of research into how to, fix nitrogen, put it in a form where it has bonds to something. Because ammonia deposits guano deposits rather, are pretty rare. And wars have actually been fought over guano. Look it up. It's happened in Peru. So Germany needed ammonia. And some German scientists, the Haber and Bosch guys, they invented this process to make ammonia out of hydrogen gas and nitrogen gas. And we're going to look at how this is balanced in our little stoichiometry exercises. So stoichiometry, as I said, is a calculation of quantities in chemical reactions. And essential in this is the mole. So again, if you're a little unfamiliar with the mole, now is a good time to go back to chapter 10. Yes, it's a whole bunch of math, and yes, that's what chemistry can be. So first, I want you to balance the Haber-Bosch process. So use that equation and take a moment to balance it. Just pause this. And you'll see that it's 3H2 plus 1N2 is going to equal 2NH3. So remember that 3 to 1 to 2 ratio for the remainder of this because that's going to matter a lot. First off, we can balance the number of atoms. Remember that Dalton's law states that the number of atoms is conserved in all chemical reactions. So I want you to look at the Haber-Bosch process again. So look at your balanced equation and just count the atoms on each side. And you're going to see that there are the same number of atoms on each side. And that's a good thing to double check when you're doing stoichiometry, is making sure that you're not somehow losing or gaining atoms. We can also balance the number of molecules. Now again, that 3 to 1 to 2 ratio, you might think, well, the number of molecules isn't completely balanced. You got 4 on one side and 2 on the other. So how is that balanced? Well, again, you look at the number of atoms, and you'll see that those do balance. And you'll see that since you're combining things into a polyatomic quantity, a molecule really, then you're going to be making a bigger molecule. Then you're going to look at the moles and the mass. So you have, again, that 3 plus 1 equals 2. That's the number of moles on each side. But if you look at the amount of mass, and you don't have mass right now, but I'd like you to take a moment to calculate how much 3 moles of hydrogen would weigh and 1 mole of nitrogen would weigh. Remember, these are diatomic molecules. And see if that matches with the amount of 2 ammonia. You're going to find it does. And that's something essential to check your math, of course, because the conservation of mass has to be obeyed when we are living in this universe. And of course, we can look at the total volume. So stoichiometry can be used to predict the total volume of ammonia gas that will be produced. So at standard temperature and pressure, which remember the Haber-Bosch process involves like really heating things up, but if we were to start at standard temperature and pressure and end at standard temperature and pressure, we're going to see that at STP, 1 mole of gas is 22.4 liters. So you can actually predict how many liters of gas you're going to get. And this is, again, one of these mathematical applications. Do you want to figure out how many atoms there are? You want to figure out how many molecules there are? You want to figure out how much mass there is? You want to figure out how much volume there is? All of these are things you can do with stoichiometry, and using the mole as a central thing is going to let you calculate all of these. So take some time to practice with this hydrogen sulfide coming from volcanic vents. It reacts with oxygen to make sulfur dioxide and water. Now remember, all of these are in gas forms, so you can use your standard temperature and pressure to calculate the volumes, and you can calculate the masses. Check your math, practice that out a little bit, and enjoy, because if you're in this class for a while longer, you're going to be doing a lot more stoichiometry.